Okay, so we have a satellite that's orbiting, has a mass of 3,400 kilograms, is traveling at a constant velocity v naught. To alter its orbit, the rocket discharges 100 kilograms of gases from the reaction of the solid fuel at a speed of 3,000 meters per second relative to the satellite in the direction opposite v naught. The fuel discharge rate is constant for 3 seconds. Determine the thrust, the acceleration, and the change in velocity. All right. Come on. So given, we have the mass of the satellite, ms, 3,400 kilograms. It discharges 100 kilograms, and it's for how many seconds? 2 seconds. So what's the mass flow rate of that? Yep. Wow, I got it right better. And it says the 3,000 meters per second relative to the satellite. Okay, so VF 3,000. Sketch. Here's our satellite. And here's our control volume. Pick the whole satellite.
Can you just pick the like main body?
Sure. Yep. Yep. And I don't know. We'll label this point. I'll just say out. Is that okay? So in space, there's no gravity, there's no forces, no external forces. And when we start the solution, I'll do it right here. Nah, I'll do it down below. I can zoom out a little bit. Just looking at the assumptions here. Anything important that I want to tell you? That's all right. So second law.
That's all you have on your diagram?
Yep. Yep. We defined a control volume and you labeled out. And there's no other forces. We have sum of the forces equals MA plus the summation of M dot V out, right? Minus the summation of M dot V in. We know that term is 0. And, oh, what are we looking for? Sorry, forgot to do finds, didn't I? Trying to find T, A, and delta V. So if we rearrange this, we have this equals what? Summation of M dot V in minus the summation of M dot V out. No,
Oh, never mind.
I brought it over to the other side. Yep.
Yeah. It's all right.
They're just defending me. Thank you, guys.
I'm so used to writing it out in. No.
What is the unit on mass times acceleration? Yeah, it's Newton. So that is what we define as the thrust. Okay. So I'm going to rearrange. I'm just going to put t equals. Do we have anything coming in? No. Which way is the satellite moving? To the right. So that's the way that we want to pick our positive direction. So we have minus m dot out, and the velocity is positive or negative? Negative. Yep. And this is actually of the, yep, that's what I'm just changing. Subscripts for you. And now we can plug it in. Minus 33.33 kilograms per second times minus 3,000. Yeah.
Question about the wording of the
Sure.
problem. So when it says and it is traveling at constant velocity v naught,
Yep.
so when it says it's going at a speed of 3,000 meters per second, why is that vf and not v naught?
So the okay. So I'm going to talk about this more when we do the next question. The satellite is going at V naught, right?
Yeah.
But the gases are shooting out at V out at 3,000.
Oh, they're shooting out at that.
Yes, the gases, the fluid gas is coming out at 3,000 meters per second.
Oh,
But the
okay.
satellite's not going that, right?
Yeah.
Yeah.
Okay. Okay. Cool.
What do we get? Yeah, sure. We'll round it to 100 kilonewtons. Not too bad, right? I teach you the fundamentals. I want to make you think in homework. Because if I do hard ones in class, no, I'll try to, never mind. Okay, find A. We know that this is true. This is the mass of the satellite, correct? Which was what, 3,400? So the acceleration is 29.4 meters per second squared. 95% of students probably are in dynamics or have taken dynamics, right? So once you know acceleration, what can you find for anything else? Everything, right? Velocity, how far it's traveled. Kristen's back there just smirking. That's funny. It's nice to look around and be like, oh my God, I know how to do this now. Not saying you didn't before, I'm just saying everything's hopefully making sense. Times 3 seconds. 88.2 meters per second. Because initial velocity was 0, right? I think. Yeah. So you see how we went from 0 to 88 meters per second as soon as we turned the things on. The what do they call them?
Well, in 3 seconds.
The discharge. Yeah, in 3 seconds. In 3 seconds. Yeah. Because that's how long the thrust was on. 88. That's good.
80 miles an hour. Yeah.
What's that?
1026, isn't that projected?
Oh, is it?
Technically,
Nice.
yeah.
Awesome.
It's like 2015 though.
Yeah, well, it's cool.
Yeah. It was cool 2 years ago.
What's it called? Huh? What's that? Like Back to the Future Day? Like,
This 2 years ago at this date,
Yeah, it's when they went back to the
they
future.
went back. Yeah, but they went forward too.
Or-
Yeah. To the future. To the
We
future.
don't have a DeLorean.
I wish.
You know Back to the Future when you're stuck in the past.
Okay. Questions on this one?
Time travel gets weird.
I don't think it's possible.
I know, but it's still weird to think about it.
I know it is weird.
I'm gonna go back to the past for the past.
All right,
I'm not,
continue in the future. Moving control volumes on Earth. It's a little different in space because.
We can connect the board.
Yeah, yeah. All right, if we have an airplane, just a simple diagram here. We'll just quickly talk about relative velocity. So, beep, 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 beep. So the plane is our control volume. I can just put V of the gas. That's fine for now. So we know on an airplane, it could be moving to the left, and if it's a jet that has exhaust gas going out, right? So if we were on the Earth looking, we would see those two things, right? But if we were on the nozzle of this, where the gas shoots out, you would see a different velocity, right? So the velocity of the gas with respect to the control volume is the velocity of your gas subtract the velocity of the control volume. It's just relative velocity, yeah. So just think of it this way. If the plane is going that way, positive direction, and your gas is going in a negative direction, right? You would actually, if you're the person sitting on this nozzle here, it would look like it would be coming out fast, right? Because it would be a negative and a negative. You would add them up, okay? Because one's shooting this way, the other's shooting that way. You're on it. You're moving this fast, and that gas is shooting out that way. At that speed, it's going to be actually going a lot faster. Okay, you kind of add these two. So this is the key thing that what we need to find in our equation is the velocity of the gas when we do the next question. Okay? So just remember this kind of concept. It's just relative velocity. All right, so let's do the next problem here. This one, it's 3 pages for me. So, but I think we can do it in less. All right, so flip your page here, and all right, I hope you can read it. Water enters vertically and steadily at a rate of 10 liters per second into the sprinkler. Shown in this figure, both water jets have diameters of 1.2 centimeters. We're going to find the omega, okay, the rotational speed, or n dot, which we'll call it later, if it's just free spinning without any friction forces. And then we're going to find the torque required to keep the sprinkler from rotating. All right? So if you notice, water is coming in from the center, right? Comes kind of out of the page, and then it splits into these two, and then that's why we get the spinning motion. All right? So let's write our givens and do all this. Oh yeah, V dot, thank you. Yep, V dot. Actually, it can be monkeys, right? As long as your units are consistent. Right? I don't know, you can call this monkey. Sure. Don't matter to me. As long as you have a nomenclature.
Didn't one kid do that for your electronics class?
Yeah, one of them did, yeah. Oh yeah, and then he had like a page and a half of nomenclature. I think Alex did it, and then Chris Newtown did it once. Yeah. No.
I remember for our final project for vibrations, we had Miss Dan and Chris, they just kept saving every file as dumbass one, dumbass two. Oh my god, I forget what's the idea in there.
here's my quick sketch, and here's our control volume. Now you can pick this control volume, or you can pick the circle that it actually makes. It's not going to matter. It's the same thing, because you're still looking at what's coming out and what kind of comes in. Let's see here. Purple. So we're going to label this point 1, this point 2. It's spinning this way. And we're going to define initially a torque, T, that way. And let's do brown. Call this theta 1 and this theta 2. What are some things that we can? Yep, they're the same. Yep, but I'm just going to define them as those. So did I write assumptions? I did do assumptions. Good. We're going to find the omega and then the torque. I'll do assumptions here. Steady state. Actually, all of these problems you've noticed are all steady state, right? We're going to neglect any drag or friction forces, because it just makes the problem even harder. The P1G equals P2G, and we're just gonna, it's going to atmosphere, right? So I'm not even going to put the pressure forces on here, just because hopefully now it's drilled in your head. You don't have to. And the velocity coming out at 1 and 2 are the same, right? All right. Questions on this? Seems okay so far? Okay, now let's get into the solution. So we're still going to do second law, but it's angular momentum, right? So the sum of the moments equals sum of the moments out for velocity, sum of the moments in. So remember what I told you when we did the airplane? This velocity is the velocity of the jet relative, or sorry, velocity of the gas relative to like on the earth, not on the nozzle. Okay, so we're going to find that. I'm going to talk about that. All right. So that's what I'm going to draw right now. This, you don't need, oh, I mean, this might help you if you do it in homework, but I'm going to re-sketch. I'm going to do it right here. This is, oh.
You're doing one side.
Yeah, I'm only doing one side. I want to just make sure it's nice and neat for you.
So we'll just generalize both sides by that one.
Yep, yep. So here's one side, and this is the velocity we're just going to define as V1 coming out. Now, whoa, how did I draw that with my finger? We're going to break it up into this component, up and down, straight up and down, okay? This is your velocity of the nozzle or the sprinkler, right? Because the sprinkler is actually rotating this way, right? This is your tangential velocity, okay? Does anybody remember what that equation was in physics? Tangential velocity? if you know omega and you know the radius? I'll give you a hint there.
I guess you use omega and radius.
Yes. You just multiply them, R omega?
Yeah.
Okay, so we'll get to that. We'll get to that. And I'm going to break up, might as well do this in light blue, this component right here. This would be V1 what? Cosine theta? So far, so good? Okay. What did I do first here?
In the X direction, whatever.
Yeah, we're gonna look at these directions. I'm gonna assume that up is positive, okay? So before I show the relative velocity, we're gonna first find V1. And we're gonna use conservation of mass. So the volumetric flow rate in equals volumetric flow rate out. Is that valid? Why is it valid in this case? Because it's incompressible. Yep. Because it's water. Yep. Density's the same. Perfect. So V dot N equals, there's two coming out, right? Is the area the same on both? So therefore, I'm going to write it, I'll do complete notes here, just to make sure it makes sense to you. So all this means is that there's two AV. Or, in a sense, 2 times V out, right? So V out is just V dot N divided by 2. So it's 10 liters per second times 1 meter cubed over 1,000 liters times 1 over 2, and you get 0.005 meters cubed per second.
These are all dots.
Correct. Yes. Not the V, not these ones. I'm underlining in red, Ben.
Yeah.
Those are velocities. So. So that's the volumetric flow rate coming out at each nozzle sprinkler head. Okay? Now, V dot out 1 equals A1 V1, correct? So let's solve for V1. A1, this is V dot out divided by what? Pi over 4 D1 squared. And let's plug these in. It just converted. 44.21 meters per second. How are we doing on time? Oh, we're doing actually pretty good on time. Bless you. Questions? Bless you. What we just found is actually the relative velocity of the jet, the little area there, respect to the nozzle or the sprinkler. Okay? The reason is because this volumetric flow rate is of the coming in of the nozzle, and the area is the area of the jet. Okay, so the biggest thing just to remember is that this actually is your relative velocity. Okay, this is what if someone was standing at the exit of the sprinkler and was spinning around, this is what the velocity they would see. This wouldn't be what the person on the ground would see. Okay? So, let's go back and let's find the velocity of the jet, which is the velocity of the person on the ground would see of the gas coming out. Okay, because that's the velocity we need to use in our equation.
Is it relative to?
To the sprinkler. Okay.
You're sitting on the nozzle.
Yep, you're sitting on the nozzle or you're sitting on the sprinkler.
Like, or like right at,
Sprinkler.
it's like, you know, you sit right at the point of the column.
Yep,
It's the relative velocity.
right here. If you go back to this sketch, you're sitting at this blue dot right here. Yep. Okay, and it's spinning around. You would actually see that velocity coming out there. Okay?
But if you're standing, just like,
But if you're standing on the ground, that's the velocity you would actually see. Okay?
so why couldn't we find like, with these calculations? What we did.
Because that's this velocity right here. That's the relative velocity. V1 is the velocity if you're standing on this X right here.
Yeah,
Okay? So we have to, if we know the velocity of the sprinkler or the nozzle, which is this one, and we know this one now, we just found it, what we can do is what? Rearrange for it? So, let's Vj equals V1 cosine theta. So I substituted in the relative velocity for V1 in our new coordinate up and down. Okay? Because these are still vectors, right? But now we're only looking in what direction? Up. And what did I say the velocity of the nozzle was?
we know the relative velocity.
No, we know the velocity of the sprinkler, right? What did I say about 5 minutes ago? Two variables.
Oh, like omega and the radius?
Yep, yep. So the nozzle is omega r. What direction is that going? Positive or negative? Negative. Negative. Compared to our what? Coordinate system? So the only thing that really you have to remember is the velocity that was given, or what we found, was really the relative velocity. Okay, because we're actually using the jet area. Okay. And we're using the incoming from the nozzle here. Why isn't that writing? Okay. So, once we have that, what can we do? I'm going to rewrite this so we have it here. So the one on your homework is pretty much identical. I just wanted you to redo it and make sure this completely makes sense. Which way do you want to do your moments? Is this okay if I do it positive? It's counterclockwise?
That'd be great.
Yeah.
So U times R, that's velocity.
Yep. R omega? That's your tangential velocity. We'll cover that at the end of dynamics.
No, it's fine.
Yep. Did you do it in physics though?
Yeah, I did. But just you could have to.
Okay.
I'll let you know in the-
What is our, so on the left here, what do we have? What do we do on our sketch? So we're taking the moment kind of right here. T?
That is some of the moment for which part?
We're taking the moment right here at this point.
So wouldn't the moment be equal both sides?
Equal?
Or you do it for one side times 2?
Yes, we'll get to there, yes. So we have negative t, right? And then we have minus r1, we'll do, there's 2 out, right? M dot 1, v of the jet 1, plus negative r2, m dot 2, v2 of the jet.
What does that mean?
I'll go back up to the sketch and show you.
What is negative gradient?
They're not.
I mean,
It's the moment that's negative.
You said the,
So my positive coordinate system is here. Okay, so if I scroll back up to this one, I said positive is this way, right?
okay. Is it really spinning to the right?
It's going, it's spinning this, it's spinning like omega is, the purple here. It's going counterclockwise.
Oh,
Okay, so our velocity is this way, right? Up.
oh,
Okay, so this goes this way, right? And then down here, it's down here, right? So that goes that way. So they're all negative. What did I do here? Do we know that R1 equals R2, right? And we know that V jet 1 equals V jet 2? And what's M dot 1 plus M dot 2 equal?
M dot total.
Yep. Yep. M dot N? They have to, right? For conservation of mass. So, combining them and making it easier, we get this. The torque is the radius times your velocity of the jet times m dot total, or m dot n. And I'm going to write it one more way. T equals r dot m dot n times v1 cosine theta minus r omega. Because I just substituted in what the velocity of the gas would be on Earth, or the reference frame. Oh, look at the mosquito. Hey, I caught it.
Nice.
And I killed it.
Dr. Craig, could you re-explain?
Right here?
Yeah.
Yep. So we know the radiuses are the same, right? Okay. And we know that the velocity of the gas based on a reference frame has to be, they're the same.
Yeah.
Okay. Okay. And we know that m dot 1 plus m dot 2 equals m dot total. So I just factored it out. So I just factored, there's t on this side. I know that R1 equals R2, so I can factor that out of the parenthesis. And I know that V jet 1 and V jet 2 are the same, so I just call those V jet. So then you have m dot 1 plus m dot 2, and that's m dot n.
this is the amount of water you put in this one.
These two are out. Oh.
This is one that's coming out.
So m dot 1 and m dot 2 are out. But based on conservation of mass, m dot in equals what? M dot out. You have m dot in equals m dot 1 plus m dot 2. Yep. So you can combine those two to get m dot in. You don't have to worry about. You could leave them as m dot 1 plus m dot 2. Sure. Yep. I just simplified it.
Shouldn't that be a positive RW?
No.
Or can?
Here.
Yeah, because when you rearrange, it'll be negative times negative. No?
Negative times a negative.
Like, flip them for this.
No. This velocity here is based on this term here. Yep. Why was the negative here? Because that's the way, we'll scroll up here, that's the way, so this thing is moving that way, right? No, the sprinkler's moving that way.
Yeah.
Oh, that's what the nozzle or the sprinkler's moving. Up there, V1 cosine theta, what'd I say this was? Relative? Yep. Okay. So the actual jet is there, right? Because it subtracts, so it's smaller. Other questions? So let's look at this equation here. What happens if there's no friction force whatsoever? Is there a torque? It's spinning really nice freely. There's no torque. Okay? So at free spin, there's no friction force, nothing. T equals 0. And what happens now when you plug in 0 on the left? You can solve, because V1 cosine theta equals R omega, based on an equation. Right there?
Wouldn't that T be R VJ, R velocity of jet, M1 minus M2? Because you changed it all to, you changed the symbol and everything, so it would be that minus that. So you'd have M1 minus M2, right?
No. I'm going to put arrows here.
Yeah. Yeah.
They're all negative. So I just changed them all to positive. Yep. Yep.
I don't have that plus sign in there, it's a minus.
No. Yeah, you could still have negative. It's still fine. Yep. But they're all negative, so they just switch signs. Just times everything by -1. Yep. So you'd end up with this, Ben. Okay. So at free spin, V1 cosine theta equals R omega. And therefore R omega equals V1 cosine theta over R. This was what, 44.21 times cosine of 60 divided by 0.4 meters. 55.26 radians per second. Question, or are you guys okay? How do we find revolutions per minute and dot? Remember? Yeah, you guys are getting closer. And we need to do something. We need to multiply by 60, right? Yep. I think. No, divide by 60. Sorry. So n dot equals omega times 60 over 2 pi. And you end up getting 528 revolutions per minute. 528 revolutions in a minute.
Is that 60 seconds?
Yes, that's the conversion to minutes. Yep. And what was the last part B? Define T when omega is 0. Because there's a torque, right? That's what the torque is defined as. So T equals R.
What do you do when omega is 0?
You just plug in 0.
But why?
Why? I don't know. Maybe it's stuck.
Oh, it was, oh.
I want to know what the torque is generated, yeah, or the amount of force. You know the radius, right? Yep. Yeah.
What's in the denominator of that omega? The 2 pi. And
60 seconds.
60 seconds.
I'll just put 60 here. Yep. Yeah. So, for example, if omega is 0, water's shooting out, but it's stuck somehow. Yep. So you want to design this based on this, right? Because if you know this torque, you can actually determine what material or whatever you want to use. So that's 0, and you plug your numbers to 0.4 meters, 0.01 meters cubed per second, times 1,000 kilograms per second, times 44.21, times cosine 60.